It's my pleasure to present the paper Do You Know Your Biases? A Monte Carlo Analysis of Dynamic Panel Data Estimators, which is joint work with Vadim Kufenko from the University of Hohenheim. The starting point for our paper is the observation that many studies in social sciences and also in economics are not replicable or turn out to be not replicable. And even if they are in terms of the sign of the coefficients, sometimes the reported effect sizes differ vastly across different studies. To give some examples from macroeconomics, if we want to know the size of fiscal multipliers, which is an important question from a policy perspective, then the estimates you get range from negative values, even which would mean that fiscal policy is not only useless but also harmful, up to values substantially above 3, which would mean that fiscal policy is very potent and should probably be enacted as a response to slowdowns. Now, of course, such a large range is not really helpful for policymakers. So that really doesn't allow them to base their decisions on sound empirical analysis. A similar issue is present in the study of economic growth, the convergence regressions that were popular in the 1990s and 2000s, where a meta-analysis by Abreu and co-authors in 2005 showed that actually the speed of convergence that is estimated across countries ranges from negative values, which would actually imply divergence across countries in terms of per capita income, up to a value that is a maximum of 65.59%, which would be very fast convergence, almost immediate convergence. Now again, such a huge range, of course, is not informative. We know some of the problems very well that lead to these non-replicability results and the issue that coefficient sizes differ strongly across different studies. And one of the most important issues is p-hacking or kitchen sink regression, so the slightly different issue of the garden of forking paths, where in general people might try lots of different specifications and then only report the one that fits to their theory in the paper, but the readers do not know how many different specifications have been tried before, or for that matter, with which decision the person who did the analysis started in the first place and which decisions he or she made on the line to getting the results. Now that's a huge issue. It's discussed quite a lot in the literature, and definitely it's responsible for a lot of these problems that we have. Then, of course, issues related to measurement errors and missing data, or imputation methods that use statistical tools that are later on used to estimate something on the same data set. Also, that leads to biased results or differences between different studies, of course. In economics, we know very well all the issues that arise with spurious correlations, endogeneity, and with omitted variable biases. So I do not need to repeat them here, and of course also with sample selection. But we would want to draw the attention to, and think that this aspect is often underappreciated, is that even the choice of the estimation method has a huge effect on the outcome. Even if we can abstract from all these issues that I mentioned at the beginning, even if we have similar specifications, no omitted variable bias, no endogeneity, no reverse causality, and so on and so forth, then just choosing a different estimation method, and we will see even one that is deemed to be unbiased under the given circumstances, might nevertheless yield to very different results in the end. And of course, it could happen in applications that this leads to the desired outcome, because somebody might just choose a method, an estimation method, that fits best to the theory that the person had before. So the particular research question that we want to answer with our paper is how large the bias of standard state-of-the-art panel data estimators are. And here we focus on estimators that are frequently reported in the literature and frequently used. We also want to address the question to which extent this emerging bias can affect the final results and in which direction. And probably we can use this information then to help identifying suitable estimators to the given questions at hand. What is our research design? What we do is we generate an artificial dataset with a true known underlying autoregressive coefficient. For this purpose, we use a simple, well-known economic growth model that generates such a time series that is still stationary in the end. Now, from this data set, we know the true underlying autoregressive coefficient because we imposed it on the data. And then we use the data set to estimate this autoregressive coefficient with the different estimation methods that we want to assess. And then we can assess the biases of these different methods. We evaluate this bias and we change the scenarios, the underlying scenarios. Namely, first of all, the true underlying autoregressive coefficient. So we start with a high value, which means a low speed of convergence actually in economic terms, so that poorer countries would catch up with richer countries at a lower pace. And then we increase the speed of convergence, which means that we decrease the autoregressive coefficient to a very low value. And we assess the estimators and how well they react to these changes in the true underlying autoregressive coefficient. Then we also change the different sample sizes in terms of the cross-section dimension, in our case the cross-country dimension n, and the time dimension t. And we will see that also this changes the relative performance of the estimators quite drastically. So some estimators that might be well suited for a high autoregressive coefficient and a small number of countries might perform worse than others in case of a small autoregressive coefficient, but a higher number of countries, and so on and so forth. And then we use the different estimators with the different properties. For example, in case of the system GMM estimator, we assess the one with the full set of instruments and the one with the collapsed set of instruments. How is this different from the paper of Hauck and Vassiak that they published in 2009 in the Journal of Economic Growth that also analyzes different dynamic panel data estimators on a convergence data set? Now, what we do is we keep the data generating process completely distinct from the empirical estimation process. So we use a purely theory-driven way of generating the data set by simulating this economic growth model, as I said before, and as I will describe in detail in later slides. And the fixed effects in our case are also not estimated, but added to the simulated data based on draws from normal distributions. So we do not have any estimation involved in the generation of the data generating process. Then we assess additional estimators, the quasi-maximum likelihood estimator, the nonlinear GMM estimator, so the GMM estimator with nonlinear moment conditions, and so on and so forth. But the most important one, I think, is the LSDVC estimator. This is the corrected fixed effects estimator. So this stands for least squares dummy variable corrected. And this estimator has been proposed in the mid of the 2000s, basically. And as we will see, it's important to include this estimator in the analysis because in some of the cases that we have, in some of the scenarios, this estimator indeed performs best. Then we assess different sample sizes, as I said before. So we change the cross-country dimension and the time dimension according to sizes of data sets that researchers in macroeconomics are usually confronted with. So for example, we might have a situation where we end up with 150 countries and 50 years, which would be a typical data set when we use the World Development Indicators. But we also assess smaller data sets. For example, if we restrict our attention to OECD countries, then we might end up with only 30 countries. Or if we restrict the time dimension to the time after the fall of the Iron Curtain, in which case we would only have 25 years for the estimation. And we will see that basically this changes quite a lot which estimator performs best and which performs worst, and it also changes the relative performance of the different estimators along the way when we change the different dimensions. And then, as I also said before, we assess different speeds of convergence, or we assess the different estimators in terms of different autoregressive coefficients. And here we see that one estimator that performs comparatively well in the paper by Haug and Vasyag, the between estimator, actually does not perform that well for other speeds of convergence. So basically it does not react to the speed of convergence when we change it. It always gives the same speed of convergence, and that is a bit like the clock that is broken, but it still gives the correct time twice a day. It's a little bit similar with respect to the between estimator that fits well in case of low speeds of convergence, but fails completely in case of higher speeds of convergence. Let's start with the description of the data generating process. Here we use a solo growth model to generate trajectories for different artificial countries I at different artificial time periods t. Now the solo model is a simple framework that generates such a time series that converges across the different countries, which means that the different time series for the different countries will be stationary. They will all converge to a balanced growth path. And that by design means that the autoregressive coefficient of these time series will be between 0 and 1, meaning that countries converge to each other. So the poorer countries with respect to their steady states will grow faster than the richer countries. Now here we assume that output of artificial country I at artificial time t can be described by a Cobb-Douglas production function with physical capital, so machines and so on, as one input in the production with an output elasticity of alpha, and labor being the second input in production with an output elasticity of 1 minus alpha. And then we assume labor augmenting technological progress. So AT here is the stock of technologies, and it multiplies with the number of workers. So newer technologies make labor more productive, and that means that we have a well-behaved convergence to the balanced growth path, and in the long run the countries will grow with the rate of technological progress. Now we have to specify how these components evolve. For technological progress, we assume that it is constant and the same across all countries at rate g. So technology progresses at rate g, which is the same for all countries and the same over all time periods. Now that is simplifying assumption here that allows us to abstract from many issues that arise in real-world growth analysis, where basically the rate of technological progress is country-specific and correlated with lots of other things, for example, capital accumulation and so on. In our case, by design, it is not, and it can be perfectly filtered out by including time-fixed effects in the regressions later on, as we do with all the methods. Then the labor force, which is in the basic solo model equivalent to the population size, grows at rate n. And here we assume that this is country specific. So we have a growth rate ni for each in artificial country I, and we draw this growth rate from a normal distribution. So that means we introduce country-specific heterogeneity here, which implies that countries will converge to different balanced growth paths in the end. Now, the important thing here is, however, that the population growth rate is different across countries, but not across time periods. So it stays constant, and that means it can be perfectly filtered out with country-specific fixed effects, which we also include in the regressions for the different methods, or we use methods that estimate inverse differences, which wipes out the fixed effect. So in any case, these differences in population growth are accounted for when we use fixed effects or first differencing. And then we have the most important component, the evolution of the capital stock. So it increases with gross investment, which is the investment rate or the gross saving rate multiplied by total income. So that is what the economy saves or invests. Then we have capital carried over from the previous period. and then we have the part of the capital stock that depreciates between period t and t plus 1. Now, the depreciation rate is again assumed to be the same for all countries and constant over time. So this is again perfectly captured by the time fixed effects. And the saving rate as I differs across countries is again drawn from a normal distribution, but is constant over time. So it's captured by the country fixed effects. Then we can easily solve for the steady state as done in the standard Solomon model with technological progress. So we divide capital by the number of efficiency units of labor, that's the number of workers multiplied by the stock of technologies, and have the transformed variable capital per unit of effective labor, which we define as K hat. Now the evolution of K hat is approximately given by gross investment in terms of capital per unit of effective labor, which is basically the gross investment rate or the gross saving rate multiplied by capital per unit of effective labor to the power of alpha, which is output per unit of effective labor. And then we have the capital per unit of effective labor that we carry over from the previous period. That also adds positively to next period's capital stock per unit of effective labor. And it decreases with respect to capital depreciation and effective capital dilution. So we have capital dilution here in terms of population growth. And we also have the growth rate of technologies here because K hat is defined with the stock of technologies in the denominator. And therefore, we also have that G itself affects K hat over time negatively. So I call this effective capital depreciation and capital dilution. Then we solve for the steady state by setting capital per unit of effective labor equal at time t and time t plus 1, which allows us to derive the capital stock per unit of effective labor at the steady state, which is then a positive function of investment. This is clear in the Solomon model. If more is invested, then this yields a counterclockwise, a clockwise rotation of the gross investment curve, and that means the intersection between the gross investment curve and the capital dilution and depreciation line is at the higher steady state capital stock per unit of effective labor. And it decreases with effective capital depreciation and capital dilution, which in the model is a counterclockwise rotation of the depreciation line, and that leads to a lower intersection of the gross investment curve and the depreciation line, so at the lower capital stock per unit of effective labor. So we see saving increases the capital stock per unit of effective labor and population growth decreases it at the steady state. Then if we raise this to the power of alpha, we get total output per unit of effective labor. So this would be this term here, and then we would just have alpha here. And if we, in addition, multiply by AT, the result, then we get output per worker or output per capita at the steady state or along the long run balanced growth path. So we see here, this would be this expression to the power of alpha multiplied by technologies. Then we are at this expression here, and we see this grows over time according to technological progress, which is filtered out by the time fixed effects. And this term here changes across countries due to the fact that we draw different values for the different countries from a normal distribution, but it stays constant across time. So this difference across countries is filtered out by the country fixed effects. Now we have basically all the ingredients to simulate trajectories for the different countries, but we still need an initial condition, so we have to start somewhere with our trajectories. And here we assume that we draw a difference to the steady state, di, from a truncated normal distribution such that this difference lies in the interval from 0 to 30%. So we multiply the steady state capital stock by this di such that we get initial capital stock per unit of effective labor. Now, why do we draw this variable such that it lies between 0 and 30%? The reason is that we later on add error terms to our deterministic trajectories, basically as they are at the moment. However, if we draw here something that is very close to the steady state and then we add an error term, it might be that the country ends up above its steady state, and then there would be convergence from above, so the country would actually shrink in terms of per capita GDP towards the steady state. Now, this would not pose a problem for our study, but we wanted to keep things as simple as possible and wanted to ensure that the countries start out with a low capital stock per unit of effective labor such that there is convergence from below. Nevertheless, we then later on use a certain burn-in, so we throw away the first observations such that we are already rather close to the steady state, such that the approximations here can be thought of capturing reality already comparatively well. So in this case, we have the model-driven fixed effects. As I said before, they are given by the differences in saving rates, population growth rates, and this initial condition or the determinant of initial conditions, this DI across countries, and that's purely model-driven. And now we know that in such a situation, the true underlying speed of convergence is approximately equal to 1 minus the output elasticity of capital multiplied by the effective capital dilution and depreciation term here. So this would give us the true underlying speed of convergence that we know because we impose it on the data set by choosing the different parameters. Now, later I will show that we then estimate the speed of convergence and compare the true speed of convergence that we know from here to the estimated speed of convergence to assess the bias of the different estimators. To do this simulation, we need different parameter values. First, I described the parameters that are basically set for all the scenarios. And here we have the first is the difference to the steady state that we draw from a normal distribution with mean 10% and variance 0.15 squared. And we truncate it such that it lies in the interval from 0 to 30%. Then we draw a saving rate with a mean of 0.2797, which was the mean that we found in the World Development Indicators database at that point. And the variance is also the same, which then in terms of our draws leaves us with draws from 2.66%, that would be a country with a low investment rate or a low saving rate, up to the maximum of 61.09%. So that's a huge saving rate, and that would probably be too high from a plausibility perspective, but could capture some countries at some time periods. So China, for example, had a very high saving rate, and Japan also at other time periods. Then the population growth rate, we draw it from a normal distribution with mean 1.8%, which is again the mean that we found in the World Development Indicators, and the variance 0.0117 squared. And this leaves us with a population growth rate between 0 and 8.37% actually, where again we truncate the results such that we do not have to deal with negative population growth rates. And then of course we would have deterministic trajectories, but we add error terms to that, but well-behaved error terms with mean 0 and the variance that is constant over time. So adding these error terms should not introduce any problems actually, so they are well behaved, normally distributed, and actually these error terms should then in the end also be the error terms of the estimation. Next, we come to the parameters that actually affect the true speed of convergence or the true underlying autoregressive coefficient. So these are the output elasticity of capital, the depreciation rate delta, and the rate of technological progress G. This is the true speed of convergence. It's calculated on a yearly basis, and this is the true underlying autoregressive coefficient, which is calculated on 5-year average basis, which is usually done in the data. So we usually work with 5-year averages in growth econometrics to smooth out business cycle effects. Now, what we have is we start with a scenario that leads to a very low rate of convergence, 1%, or an autoregressive coefficient of 0.95 approximately. And this is achieved by having a comparatively high value of alpha, of the output elasticity of capital, and a comparatively low value of the rate of depreciation delta and the rate of technological progress G. So now if we impose these parameter values, which would not be parameter values that economists who calibrate models would usually use, because alpha would be higher than the one that they usually impose, and delta and G would be much lower, but it leads to the first scenario that we want to assess. And then step by step, we decrease alpha and we increase delta and G, such that until the 10th scenario, when we have a very high rate of convergence of 8.45% or an autoregressive coefficient of 0.6554. In this case, we would have rates of depreciation and technological progress that are already much higher than the ones we would usually assume, and an output elasticity of capital that would be much lower than the 1/3 that is usually imposed in the literature. Now, one could identify one specification or one scenario here that yields quote-unquote realistic parameter values. So that would be scenario 7. It would have a growth rate of technologies of 1%, which is often assumed, a rate of depreciation of 5%, and an output elasticity of capital that is close to the 1/3 that usually comes up in the literature. However, it's important to mention here that we do not need to choose realistic values because the only thing that we need to know is that we know the true underlying speed of convergence. It doesn't matter whether it's high or low or reasonable or not. It's just important that we change one. Select one. In the end, however, when I will talk about a baseline specification, I will usually refer to this one here with the reasonable parameter values. Finally, we come to the specification of the sample sizes. And here we consider, as I said before, 4 different scenarios that are quite similar to the ones that researchers in the area of macroeconomics are usually confronted with. In the first scenario, we have a time dimension of 10. Since we average over 5 years, as it is common in the literature, this means that we have data for 50 years. And then we consider 150 countries, which would typically be a data set with which we end up when we use the countries from the World Development Indicators database, because for many countries the data are missing for certain time periods. Then, however, we also consider a second scenario in which we decrease the number of countries substantially, and this might be a situation when we focus on OECD countries, for example. In the second scenario, we only have 10 countries, but still the same number of time periods as in the first scenario, namely 10. Then in the third scenario, we again have 150 countries, but we restrict the time dimension to 5. So that would mean 25 years. And that could be, for example, a situation when we focus on all the countries in the world, but after the fall of the Iron Curtain. Or it could also be the case if we include a certain variable for which we have the data only for later time periods, that we end up with such a sample size. And finally, we consider both restrictions, a shorter period of time and a smaller number of countries, and that would be a restricted sample of OECD countries for, say, after the fall of the Iron Curtain, so for 25 years. Now this picture illustrates the simulation paths for one particular simulation run over the 10 scenarios that I've described before, for the case of 150 countries and 10 time periods. Now what we see here in the first scenario is a low growth rate, because the rate of technological progress is rather small, and therefore the trajectories for the countries are rather flat, and convergence takes quite a while. And then as we move on to scenario 10, there we would have steeper trajectories. The growth rate of technologies is higher, so therefore the long run growth rate is higher, and we have faster convergence to the balanced growth path. So here we see that after 5 time periods or so, these lines move in parallel, while here it takes a little bit longer. As I said, we exclude the first periods for estimation, and that should allow us to come closer to the steady state. And what I also have to say at this point is that we do not only do one such simulation run, but instead we do one simulation for the 10 scenarios, then estimate the parameter, the autoregressive coefficient for all of these 10 scenarios, and then we repeat it with a new data set. So we generate a new data set and do the same again, and we repeat this 1,000 times. The reason is that we can get rid of things that happen by chance in doing so. After we repeat all these processes, we get a distribution of the true underlying speeds of convergence across the different scenarios. And what we see is that this is nicely behaved. So we have normal distributions around the true value that we have, and the variation is rather small. But that helps us to kind of smooth out results that would be just due by chance. After each iteration, we compute 5-year averages, as it is standard in growth regressions to smooth out business cycle fluctuations, and then estimate for each iteration the logarithm of per capita GDP in the current 5-year period on the lagged per capita logarithm of per capita GDP in the previous 5-year period, where this parameter gamma here is the autoregressive coefficient that we want to estimate. We include time fixed effects, we include country fixed effects, and we have an error term that should be well behaved in the sense of having mean 0 and a constant variance covariance structure. Now, when we have the estimate of gamma, we can then reconstruct the estimated speed of convergence, which is just given as, so it gives the autoregressive coefficient as e to the power of the negative of the estimated speed of convergence multiplied by the time periods over which the speed of convergence is calculated. And we can reformulate this such that we have the speed of convergence, the estimated speed of convergence, isolated on the left-hand side as the negative of the logarithm of the autoregressive coefficient divided by the time periods. And now we compare this estimated coefficient to the true speed of convergence that we imposed on the dataset, and by this we can assess the bias that emerges from the different estimators that we use. We assess different estimators. As I said before, we have the population average estimator, the fixed effects estimator, the random effects estimator, the between estimator, the corrected fixed effects estimator as the least squares dummy variable corrected estimator, the difference GMM estimator, the system GMM estimator, a GMM estimator with nonlinear moment conditions, and a maximum likelihood estimator of the fixed effects models. Now, we include or we estimate the GMM specifications using the robust standard errors with the small sample correction as proposed by Windmeyer. And we include in the GMM specifications the period dummies as instruments. And then often it's recommended to use a collapsed matrix of instruments to address instrument proliferation, so when the number of instruments would become large as compared to the number of cross-sections n. And in our case, for the scenario with 150 countries and 10 time periods, collapsing would yield a reduction in the instruments from 64 to 20. Basically, and we implement both versions of the estimator to see also under which scenarios collapsing is a good option and under which it might not be such a good choice. Now this picture displays the results. We have here on the horizontal axis the true speed of convergence, and on the vertical axis the implied speed of convergence, where along the dashed red line the two are equal. So that would be where the true and the estimated speed of convergence are the same, and an estimator that is completely unbiased would lie the points of this estimator that this estimator provides us with would lie along this dashed red line. Now, though none of the estimators matches that perfectly, but what we can say for sure is that 4 estimators consistently overestimate the speed of convergence by a large margin, and that's the population average estimator, the fixed effects estimator, the quasi-maximum likelihood estimator, and the difference GMM estimator. And they overestimate the speed of convergence by a factor of 5 for a low imposed speed of convergence, and still by a factor of 3 to 4 for a high speed of convergence. The GMM estimator with the nonlinear moment conditions only performs marginally better, but not that much. It also overestimates consistently. Then on the other side of the range, we have the between estimator that consistently underestimates the speed of convergence. But what's interesting here is that as we increase the true speed of convergence, the between estimator always gives us almost the same estimate. If anything at all, then the estimated speed of convergence even decreases. So basically this shows that this estimator is rather useless for estimation, but, and that's the interesting thing also, here for low speeds of convergence, it just by coincidence comes close to the true imposed speed of convergence. But nevertheless, just from that coincidence, one would not recommend this estimator. And then we have two medium performers. The random effects estimator overestimates the speed of convergence for low speeds of convergence and underestimates it for high speeds of convergence. And the system GMM estimator with the collapsed matrix of instruments, there the same holds true, so it overestimates the speed of convergence for low speeds of convergence and underestimates it for high speeds of convergence. And then we have two performers that are rather well. One is the system GMM estimator with the full set of instruments. This one, it lies rather close to the true values. And the corrected fixed effects estimator, which is a little bit farther away and underestimates the speed of convergence for low speeds of convergence and overestimates it for high speeds of convergence. But, and this is the drawback in case of the corrected fixed effects estimator, for a low true speed of convergence, it would actually estimate divergence, and that's also, of course, from a practical perspective, problematic. What's interesting here is basically that when the corrected fixed effects estimator starts to overestimate the speed of convergence, the system GMM estimator with the full set of instruments starts to underestimate it. So to some degree, these two estimators almost always contain the true value between them. Now, the final thing I want to say here is that the system GMM estimator with a full set of instruments performs better than the one with the collapsed set of instruments here. And the reason being clear, because we have a rather comparatively large cross-section dimension of 150, which means that we have enough data points for the large number of instruments so that collapsing is not necessary here. We can look at this also in terms of the mean absolute percentage error, where we see that the four estimators that performed badly before, they have the highest mean absolute percentage error consistently. That's clear. Also, the GMM estimator with the nonlinear moment conditions does not perform that well, and the between estimator also has a high mean absolute percentage error, except for low speeds of convergence, but that's just by coincidence, as we already know. And the corrected fixed effects estimator and the system GMM estimator with a full set of instruments, they perform rather well across a wide range of of scenarios, but for low speeds of convergence, the mean absolute percentage error of the corrected fixed effects estimator is still high because it predicts divergence. What changes when we move to a smaller sample size? So here we see the situation for a number of countries of 30, so an OECD data set, if you will, and 10 time periods. Now, the central issues stay rather the same as before. So there are a few estimators that overestimate the speed of convergence tremendously. Now the GMM estimator with the nonlinear moment conditions is also among them, and the between estimator underestimates it substantially. But now the relative performance of some of the good performers actually changes. So the system GMM estimator with a full set of instruments now is also not very useful. It's almost the same as the between estimator here. But the corrected fixed effects estimator improved. It's closer to the true value now for a wider range of specifications, as we will also see in terms of the mean absolute percentage error. And the system GMM estimator with a collapsed matrix of instruments also got better here. And that would not be surprising because in this case, the number of countries is low. The number of instruments would exceed the number of countries by a factor of more than 2 for the full set of instruments. So collapsing in this case is advisable. Well, this is just the picture again for the mean absolute percentage error. The 5 bad performers are here, so we know they have a high mean absolute percentage error, and the low mean absolute percentage error is now here for the corrected fixed effects estimator and the system GMM estimator with the collapsed matrix of instruments, and for low speeds of convergence, still the system GMM estimator with the full set of instruments is performing well. Now we change the number of time periods to 5, and this seems to change nothing here for the bad performers. The GMM estimator with the nonlinear moment conditions are a bit better now than they are. The between estimator fails, but now the corrected fixed effects estimator comes close over a very wide range of scenarios than the system GMM estimator with the full set of instruments or with the collapsed set of instruments. So in this case, the corrected fixed effects estimator would perform comparatively well for rather high speeds of convergence. For low speeds of convergence, it still fails quite dramatically. The same here visible in terms of the mean absolute percentage error. The corrected fixed effects estimator has a low mean absolute percentage error for a high speed of convergence, but not for a low speed of convergence. And finally, we have the scenario where we have a restriction on both. The cross-section dimension is 30 now, and the time dimension 5. And this deteriorates again the performance of the corrected fixed effects estimator a bit. The system GMM estimator is performing surprisingly well for the case that we still have 30 countries, and the system GMM estimator with the collapsed matrix of instruments does not perform so well as the system GMM estimator with a full set of instruments. Well, and this can also be seen here in the mean absolute percentage error, where the system GMM estimator here and the corrected fixed effects estimator to some extent have the lowest, and here on this end also the system GMM estimator with the collapsed matrix of instruments. Now I've talked a lot about the bias of the different estimators, and I will summarize the results in a minute. But what we also are often interested in is actually the efficiency of estimation. So what we also did was, for one scenario, that's now the baseline scenario that I said before, the one with the reasonable parameter values, we bootstrap the confidence intervals around the different estimators. Now here, along this green dashed line would be the true autoregressive coefficient that for this particular scenario was about 0.77. And what we see here is the different estimators, the point estimates that they deliver, and the whiskers here display the 95% confidence interval. Strikingly, only the system GMM estimator with the full set of instruments even includes the true value in the confidence interval, while other estimators are very efficient. They are basically efficiently providing wrong estimates in this case because they are far off the target. The corrected fixed effects estimator and the system GMM estimator with the collapsed matrix of instruments, they also come close to the true value. And then as we change the dimensions of the data set, then also the confidence intervals change. So we reduce the number of countries to 30 here. And what we see is that the confidence intervals in general got wider. That's not surprising. But actually what is to some extent astonishing is that the confidence intervals of the difference GMM estimator, of the corrected fixed effects estimator, and of the system GMM estimator with the collapsed matrix of instruments, they become very wide. And now in this particular scenario, the system GMM estimator with a full set of instruments would not include the true value anymore in the confidence interval. Some other estimators would, but for the difference GMM estimator, that's not so surprising because it includes almost everything here. So in general, we see the variance increases, the confidence interval increases, the size of the confidence interval for a reduction in the number of countries, and some estimators are still very far off the true value that we want to estimate, but have a low confidence interval. Now I summarize the implications for estimator choice. We've seen that population average, fixed effects, maximum likelihood estimation, the GMM estimator with the nonlinear moment conditions, and the difference GMM estimator always perform rather badly, and the between estimator performs well only for a low speed of convergence, but not for a higher speed of convergence. So it's surprisingly good performance in the paper by Harkot might just be by sheer coincidence. The system GMM estimators perform comparatively well, but the performance depends strongly on the underlying scenarios and the sample sizes. So the system GMM estimator is particularly well suited to identify low speeds of convergence, and it is if we have the version with the full set of instruments, then this works well for a large set of countries, but for the version with a collapsed matrix of instruments, it's better if the sample size is smaller. So yeah, the recommendation would be in line with what we know from these estimators. And the corrected fixed effects estimator also performs comparatively well, particularly for a medium to high speed of convergence and a small number of countries, but one should not recommend it for low speeds of convergence, probably. To conclude, what can we learn from this? I think that should be a cautionary tale to those who use dynamic panel data estimators themselves, and to those who rely on the results and interpret the results. So I would recommend to be very cautious if a certain study only provides the results of one estimator, particularly if this estimator is among the ones that did not perform well in our case, even if it is deemed to be unbiased under certain circumstances, such as the difference GMM estimator. So we've seen that the difference GMM estimator essentially does not really perform that well in this case here. One should carefully choose and interpret the different estimators depending on the sample size and depending on prior information on the size of the autoregressive coefficient. So we know that the estimators and the relative performance of these estimators changes quite a bit when we change the underlying dimensions of the dataset and the underlying size of the autoregressive coefficient. And finally, the corrected fixed effects estimator and the two versions of the system GMM estimator tend to perform best, but the relative advantage again depends on the sample size and the scenario that we have under consideration. But in general, I would recommend to report them and to look at the results critically from the perspective of changing the sample size and prior information on the size of the autoregressive coefficient. This is the underlying references that I used, and thank you for your attention.